Hello everyone and welcome to this talk. Today I'll talk about learnability of PUFs and present our paper PUF-G, a CAD framework for automated assessment of learnability from formal PUF representations. This work is done under the supervision of Professor Devdeep Mukhopadhyay and Professor Aritra Hajra. I am a PhD student in the Department of Computer Science and Engineering at Indian Institute of Technology, Kharagpur, India. My research interests include learnability analysis of physically unclonable functions and design of robust PUF constructions. Let me give you an overview of the talk. First, I'll talk about a brief introduction on physically unclonable function and its application along with some example circuits. Next, I'll talk about the motivation behind this work and its necessity in the current scenario, followed by a brief discussion on the basic concepts required to understand this talk better. After that, I'll talk about the first contribution of this work, which is a formal language to represent PUF architectures. I'll illustrate the use of the language with the help of an example. Then I'll explain the most important component of this work, which is a CAD tool to determine the learnability of a physically unclonable function. I'll go through each component in detail. This will be followed by the experimental setup and the results that we obtain from the tool. At the end, I'll give some of the important takeaways from this talk and the future scope of the work. So, what is a physically unclonable function? A physically unclonable function, or PUF, is a function embedded in a hardware which uses the intrinsic properties of its host device. Like any other function, it takes a set of inputs known as challenges and gives a set of outputs known as response. Since the mapping depends on the intrinsic properties of the host device, it makes every manufactured instance unique and unclonable. Anybody trying to make a copy of the hardware will not be able to replicate the same function behavior as the device properties will be different. This makes PUF a very interesting primitive which is used in various applications starting from authentication and key exchange protocols, device fingerprinting, even random number generation and key generation. However, these properties make it extremely challenging to determine if a PUF is good or bad. A good PUF design should be unique, reliable, unbiased, and unpredictable. To be unpredictable, a person who does not have the access to the PUF should not be able to guess its output for an input with high probability. So, one of the most popular approaches to test this property is using modeling attacks. In such an attack, an attacker has some challenge response pairs and he tries to create a mathematical model of the PUF and create the output for some unknown challenge. To satisfy this property, a PUF should be secure against such attacks. In this talk, we'll look into silicon PUFs. One of the first construction is the arbiter PUF. It consists of a series of crossbar switches, each of which has a control bit. The input terminals of the first switch are shorted and given an excitation signal. The input to the PUF is fed to these switches, which decides which path is taken by the signal. If the control bit of a switch is 0, then the signal goes to the straight path. If the bit is 1, then it goes to a cross path. Finally, the signals reach a part of the circuit known as arbiter, which decides which signal came first and decides the output accordingly. Soon after this design was proposed, it was shown that its output can be predicted using a linear model. So now the next task was to introduce non-linearity in the circuit. One of the approach was to introduce a feed-forward component. Another one was to introduce an XOR gate, which combines multiple arbiter PUFs output using an XOR gate. However, these were also proven to be learnable. Now, this brings an important question. Even the Interpose-PUF, which is one of the contemporary PUF design, was proven to be learnable. Now, this brings an important question. Is there a way to understand the merits and demerits of a circuit before implementing it? We try to address this question in this talk. In this work, we use provable learning rather than empirical learning simply because of the fact that in case of empirical learning, we are not sure that we'll get an accurate model at the end of training phase. However, in provable learning or the PAC learning model, we are assured to get an accurate model for given levels of accuracy and confidence. In case of PAC learning of PUFs, given a PUF design, an attacker tries to find a suitable representation class and a learning algorithm. Using this algorithm, it computes the number of input-output pairs needed to attain a fixed accuracy given by epsilon and with the given confidence of the algorithm, which is delta. So now, why do we need a CAD tool? The first reason is it enables analysis of PUF designs from a theoretical perspective and can be performed in a pre-silicon phase. The second reason is it acts as a helping aid of a designer who may or may not know machine learning. It also helps a designer to explore all possible combinations of PUF architectures by making analysis much easier. So a designer can iterate through multiple design choices before deciding on a good design. In this talk, we'll also need some concepts on linear threshold functions and perceptron algorithm. So a linear threshold function or LTF generates a linear hyperplane which splits the input space into two parts. A perceptron algorithm is an online algorithm which is used to learn an LTF. It takes as input some points and labels given by the LTF, and using its update mechanism, it tries to determine the position of the hyperplane in the space. The perceptron algorithm is set to converge if the number of mistakes it makes is less than the mistake bound. Note here that the mistake bound depends on the input length and the distance of each data point from the hyperplane. In 1989, Littlestone proved that an online algorithm can be converted to a PAC learning algorithm, and the sample complexity of the PAC variant is of the order of the mistake bound times the reciprocal of the accuracy. Later in 2001, Surveydo showed that the online algorithm can be transformed to a PAC learning algorithm in polynomial time with respect to the input size, the weight of the hypothesis, and the accuracy and the confidence. Now, coming back to the first contribution of this work, I'll show you the basic constructs of this language. This language has three data types: num for numeric data, vec for vectors, and bit for binary. One can create a primitive using this basic building block. So using begin primitive and end primitive, it can create any primitive. The primitives are called using primitive calls, which is very similar to a function call. This language has direct and conditional assignment statements, a serial composition and a parallel composition. Serial composition is used in designs which require components to be placed serially, such as switches inside an arbiter PUF. A parallel composition is needed if multiple primitives have to be instantiated together. For instance, in case of an XOR PUF, where all the constituent arbiter PUFs have to be triggered together. This language is actually capable of representing any PUF construction or composition. So here is the syntactical grammar of the language. So now let me explain this with the help of an example. In the case of a feedforward XOR arbiter PUF, every module is created using the primitive construct, using the begin and end structure. It has a set of statements, the input definition and output definition. So if we look at FF-XOR APUF, so here it consists of three feed-forward APUF instantiations which are called within a parallel block. The assignment, and if we look at the feed-forward delay chain, the assignment of the intermediate arbiter is done using an conditional operator, as we see here. The rest of the circuit can be implemented as shown here. Now, coming to the CAD framework, the CAD framework can be split into two parts, the front end and the back end. The designer gives the PUF design in the PUF description language. The front end generates the intermediate model and sends this model to the backend to assess learnability of the PUF from an architectural point of view. This is the complete flowchart of our tool. Now, coming to the front end, the first step is tokenization. In tokenization, it generates tokens for all the keywords and the operators. Then the parser goes through the code and generates a structure or a node for each of the primitive components, such as say primitive name, input definition, statements, or output definitions. So these are formed in a top to bottom manner. So first it will go from primitives to statements, say to assignments, then to literals. After this complete node is formed, it is added to a linked list. So finally, we get a hierarchical structure or a linked list comprising of nodes where each node corresponds to one module definition. And the head of this linked list is sent to backend for further analysis. In the backend, the first step is module identification. So a designer can represent any PUF and not just the known PUF constructions. Thus, the hierarchical structure has to be traversed to understand the components. It calls this function identify module, which traverses the structure bottom up to identify the components in a recursive manner. After the function identifies the most basic module, it calls this function learnability module, which returns a representation class. After returning to the parent identify module function, it checks here for the input and output transformations. And it does that by comparing the current module with the submodules. And the submodules are the modules which have been instantiated using the primitive calls inside. So how does this input or output transformation takes place? So if we go back to the feed-forward XOR APUF example, so inside the delay chain module, we saw that it has some conditional assignment to the arbiter output of a challenge bit. This implies there has been some modification to the input. Next, if we see the feed-forward XOR APUF module, it has FF-APUF module inside a parallel block, which is followed by an XOR. The tool identifies these structures to understand that there has been an output transformation. On seeing this input transformation, the tool changes the representation class from LTF to LTF with noise. The topmost function in the backend, which is this, calls three functions. Handle input. Handle input basically picks the numeric parameters from the input definition of the topmost module. Then identify module tells which PUF representation it is, and the compute sample complexity function calculates the expression of the sample complexity of the learning algorithm corresponding to the representation sent by the identify module function. So for LTF with noise, the tool chooses perceptron as the learning algorithm. Now, due to the input transformation, it modifies the mistake bound using the response bias calculation given in this paper. Now, after the mistake bound is modified, it calculates the sample complexity and then it checks whether the sample complexity is polynomial in the numeric parameters which we obtain from this handle input function. So the front end of this tool was developed using Lex and YACC. The backend was implemented in C language. This whole thing was executed on a 3.4 gigahertz Intel i5 processor with 8 GB RAM. And the total time taken by the tool was around 10 to the power 5 to 10 to the power 6 clock cycle, which comes around 0.3 seconds. And all the results that we obtained from the tool have been theoretically validated using proofs. We obtained the learnability results of these PUF constructions from our tool. Some of the results are existing in the literature. The remaining ones are derived for the first time using this tool. The results derived for the first time are marked by star. To conclude, the PUF representation language can be used to represent any PUF construction. It automates the learnability assessment of PUFs and enables better understanding of PUFs from an architectural point of view. As a future work, the tool can be extended to support PUF constructions using components such as TRNG, bend functions, or weak PUFs, and it can also include calculation of PUF quality metrics such as uniformity, uniqueness, reliability from an architectural design specification. That's it. Thank you for listening.